Hello, everyone, and welcome back. In the last few chapters, we were introduced to natural language processing and how we use RNNs to predict next words and convert the sentences into tokens and sequences. Now that we know how we can predict the next word, it is important that we understand how we can create some text. Imagine a book that is written completely by a machine and not by humans, has just given the context of what we want the story be like, and it creates the text of the entire image or the book by itself. So you can see the small number of lines we have. This text was generated by a very simple model trained on a small corpus. I've enhanced it a little by adding line breaks, punctuations, but other than that, the first line, the rest is generated by the model. So in this chapter, we'll learn how we can give just a single line of or sentence to the machine, and in return we get number of lines generated by the model itself. Right. In the last few chapters, you saw how you can use TensorFlow with text-based data, first tokenizing it into numbers and sequences, then that can be processed by neural network, then using embeddings to stimulate sentiment using vectors, and finally using deep and recurrent neural network to classify text. So what we have done till now is we had our sarcasm data set and we have just classified the text into if it is sarcastic or not. In this chapter, we are going to switch gears and we are going to, instead of classifying the existing text, we'll now predict some text using neural network. Given a corpus of text, it will attempt to understand the patterns of words within it so that it can, given a new piece of text called a seed, predict what words should come next. So what happens is that, what is seed here? What we're going to do in this chapter is we'll be given a word called or a piece of text that we'll call seed, and we'll predict the next word here. Once it has that, the seed and the predicted word, that will together become a new seed, and then we'll predict the next word. So, you know how we were classifying earlier. Now we'll predict the other word as well as the whole sentence coming up next. Thus, when trained on corpus of text, and neural network can attempt to write new text in similar style. To create the piece of poetry above, I collected lyrics from a number of traditional Irish songs, trained a neural network on them, and used it to predict words. So we'll start with small amount of text that we have already seen. We'll just use that, and to get started, you'll have to treat the text a little differently from what we have done so far. Like in the previous chapters, we took the sentences, turned them into sequences, and then classified them based on the embeddings for tokens within them. Now, when it comes to creating a data that can be used for training a predictive model like this one, there's an additional step where sequences need to be transformed into input sequences and labels, where input sequence is a group of words and the label is the next word in the sentence. So, for example, we have a sentence called the sky is blue, right? So the input sequence would be the sky is, while the label would be blue. You can then train a model to match the input sequences to the labels so that future predictions can pick a label that's close to the input sequence. So let's see how we can turn sequences into input sequences. When predicting text, you need to train neural network with the input sequence or feature that has associated label. Matching sequences to labels is the key of predicting the text. So for example, if your in your corpus, you have the sentence that today has a beautiful blue sky. You could split this into today has a beautiful blue as the feature and sky as the label. That I've already told you this before, right? Then, if you were to predict for today, for next text, today has a beautiful blue, it would likely to be sky. If in the training data you also have yesterday had a beautiful blue sky and you split this similarly, there is a high chance or a high probability that it will choose the word sky, because both the sentences, like yesterday had a beautiful blue sky and today has a beautiful blue sky, both have some kinds of words that are similar, like beautiful, blue. So it might relate that beautiful and blue are always related to sky. There is a high chance that it would predict that if we are talking about beautiful and it's blue, we are talking about sky. Lots of sentences training on sequences of words with next word being the label. You can quickly build up a predictive model where the most likely next word in a sentence can be predicted from the existing body of the text. Right, so we'll start with a small corpus. It's a traditional Irish song lyrics. So we just take this and yeah. So we are using \n for line break. So wherever there are full stops or something, and the whole data set looks like this, but it's actually not this. The data that we are feeding it would look like something like this. So wherever there is a comma or there is a full stop, we exchange it by \n, right? So we call in the tokenizer, we give the data, we convert the data into lowercase and then split it with \n, right? So as similar as before, we just use tokenizer dot fit on text that we fit on corpus, and then we take the total words length of the words plus 1, right? So the result of this process is to replace the words by their token values. So we can say that in the town of Athi, one Jeremy Lanningan. So it is tokenized something like this. The sentence is tokenized something like this. To train a predictive model, we should take further step here, splitting the sentence into multiple smaller sequences. So for example, we can have one sequence consisting of first 2 tokens, another first 3, etc. So you will just understand what I'm talking about here. So here the text that we converted or tokenized into the sentence that we tokenized here is here again. So it's a array of numbers and we want it to look like this. So we just convert a sequence into number of input sequence. So rather than we have 4, 2, 66, 8 and so on, we just divide it into 4 and 2, 4, 2 and 66, 4, 2, 66 and 8. So we have increased the number of sequences here. To do this, you'll need to go through each line in corpus, turn it into list of tokens using text to sequences. Then you can split each list by looping through each token, making a list of all the tokens up to it. So if you don't understand it, don't worry, we'll just go through the code and we'll understand it better. So we have input sequences, that is empty list. So for line in corpus, token list equals tokenizer to text to sequences, and we start from 0. So for I in range 1 to the length of token list, then we just take n underscore gram underscore sequence equals token list from starting till I plus 1, less than 1 actually. Then input sequences dot append and append it into ngram dot sequence, right? And then we have printed the sequence for 4 actually. So once we have all these input sequences, we can also pad them in a regular shape. So imagine that what we were seeing first, that the shape of all these input sequences is different. So first one has a shape of 2, the second one has a shape of 3. But what we want to do is we want to pad them so that they look of the same shape. They have the same shape, right? So we have padded this, and I hope you know from the last videos that how we pad the sequence using pad sequences, and we pass in the input sequence and the maximum sequence length that we can take for the maximum sequence length, or we can just choose it randomly for ourselves, right? So, and padding is pre, so we want it to be pre, and you'll understand why we are taking pre padding rather than post padding that we usually do. Finally, once we have the set of padded input sequences, you can split them into the features and labels. So how we're going to split them is, you can see in this figure that the first all zeros till 4 is our input X or the features, and 2 is our label, and simultaneously for the others as well. So for the second one, till 2 would be our features and 66 would be our label. When training a neural network, you're going to match each feature to its corresponding label. So for example, the label for this 0000042 and so on will be 70, because in the last, you can see for the last array, you can see the value or the label would be 70. So the answer would be 70 for that. So is the code how to separate the labels from the input sequences. So we have XS, that is a features, and labels, and we are just using slicing technique, and what we are doing is input sequence, all the rows and the columns except the last one, and for the labels we are just taking the last column. Next, you need to encode the labels. Right now they are just tokens, so we need to encode them. And what would happen if we don't encode them? So imagine that we have the labels starting from like minimum to like 1 to 0 or something, and it goes till 10,000. So there is a huge range of values. Imagine the probability being distributed from 0 to 10,000. Even if each of the values till 10,000 have a very small probability, the probability of the actual label would become very less, right? So the accuracy would be hampered. But if you want to use a token as a label in a classifier, it will have to be mapped to an output neuron. Thus, if you're going to classify n words, with each word being a class, you'll have to have n neurons. That is the last dense layer that we have. We'll have, if we have 10,000 words, then we'll have 10,000 neurons in the last layer. So means 10,000 probabilities all joining together to just make one. Here, where it's important to control the size of the vocabulary, because the more words you have, the more classes you need, right? So let's just skip from here and jump to the good part. Additionally, you need to one-hot encode your labels so that they match the desired output from a neural network. So consider if neural network is fed an input X consisting of series of zeros followed by 4, you'll want to predict to be 2. But how the network delivers that is by having an output layer of vocabulary sized neurons, where the second one has the highest probability, right? So if the value is 2, it's obvious that 2 will have the highest probability. To encode our labels into a set of Y's, you can then use to train, you can use the two categorical utility in tf.keras. So we want to encode our labels here. So we are encoding and storing it in ys using utils.to_categorical, and we'll pass in the labels and the number of classes are the total words. So you can see the labels of the Ys and hot encoded like these. So all the numbers or all the neurons or all the number of words or n number of words that we have, it will be only one for that where the label matches. This is very sparse representation which if you have a lot of training data and a lot of potential words, will eat memory very quickly. So suppose that you have 100,000 training sequences with vocabulary of 10,000 words, you'll need around so many large bytes just to hold the labels, right? So let's go and create a model. We know about the data, we have the data, now we just have to create the model, right? So it consists of an embedding layer followed by an LSTM layer and followed by a dense layer. For embedding, you will need a one vector per word. So the parameters will be the total number of words and the number of dimensions you want to embed on. In this case, we don't have many words, so 8 dimensions would be enough. So I hope you remember the embedding dimensions that we set earlier. Now it's gonna be 8. You can make LSTM bidirectional and the number of steps can be the length of a sequence, which is our maximum length minus 1. So LSTM bidirectional we are using and the steps can be the length of the sequence. Finally, the output layer would be a dense layer with number of words of the parameters of words as parameter activated by softmax, right? So when we compile this model, we're just using categorical cross entropy, optimized as Adam and matrix is accuracy. It's very simple model without a lot of data. You can train for a long time, say 100 and 1500 and epochs. So when we train it, we see the training accuracy is pretty good. It's actually reaching up and high and going good, reaching almost 90-95% accuracy. And we can be assured that we have a string of text that has seen it will predict the next word accurately. However, when generating a text, it will continually see words that it hasn't seen before. So what it will do when it is actually predicting and what kind of accuracy we get when predicting, we have to see that if it's producing some sensical text or not. Right, so let's generate the text next. So we have trained the model, we have trained the network to predict the next word, and let's see how it predicts. So we'll start by creating a phrase called a seed text, and this is the initial expression on which the network will base all the content it generates. It will do this by predicting the next word. So we have a phrase that it's already seen in the town of Athi, and that's the seed text. And now we need to tokenize it. So using tokenizer.text to sequences, we pass in the seed text and then we pad it as well, right? We need to do that. This will result in return probabilities for each word in the corpus. So pass the results to np.argmax. So we'll just get the value for maximum probability, right? So we get this using np.argmax. Then we have the values. So when we print predicted, you should give the value 68. If you look at the word index, you'll see that word is 1. So 68 is token for 1, right? So the predicted word is 1. You can look it up in the code by searching through the word index. So you can just pass in the word. You can pass in that value and you can get the word. So starting from the text in the town of Athi, the network predicted that the next word would be 1, which is correct. So it's a strong beginning, but this word, this whole sentence or the seed text, it's already seen before, right? Now you have confirmed that model is working. You can get creative and use different seed text. You can, for example, when I use the seed text suite, Jeremy saw Dublin. The next word it predicted was then. This text was chosen because all of those words are in the corpus. You should expect more accurate results, at least at the beginning, for the predicted words in such cases, right? So we would say that if we are getting 95% training accuracy, it should give us good results when we are giving it seed text in the form of text it has already seen, or have some words that is already present in the corpus. So with compounding the predictions to generate text, so to have a neural network now create new text, you simply repeat the prediction adding new words each time, right? So for example, earlier when I used phrase sweet Jeremy saw Dublin, it predicted the word would be then. You can build on this by appending then to the seed text and then see what the next prediction gives. So when just not doing anything, as we have already discussed for before, that we have a seed text and then we have a prediction, then we join the seed text and the prediction to get the next prediction, right? That's what we are doing right now. So this is how we're gonna get a whole predict a whole sentence rather than a single word. So we have the seed text, so we want next 10 words, right? We are just doing the same thing that we get next words in here. So that's 10, so it goes for 10 loops, and we get the token list converted into sequences, that's seed text only, and then we pad sequences, and we have already done that, and then we model.predict. So I'll just tell you that model.predict underscore classes does not work anymore. It's other than that, you can just use np.argmax and just use model.predict around that, right? So you will have to write np.argmax brackets and model.predict and just give in the token list and word rows, right? So then you just join it. So if index is its predicted words is equal to the index, so output word is word, or and you break out of it and you just add the output word to the seed text and then we predict the next word. That's how it works. It rapidly descends into gibberish. Why? The first reason is that body of training text is really small. So the training data is really small. And the second is that prediction of next word in sequence depends on the previous word in the sequence. And if there is a poor match on the previous ones, even the best next match will have a low probability. When you add this to sequence and predict the next word, after that the likelihood of it having a low probability is even higher. Thus, predicted words will seem semi-random. So, for example, while all the words in the phrase like sweet Jeremy saw Dublin exist in the corpus, they never exist in that order. So, we always know that sweet Jeremy saw Dublin don't exist in the same order in the corpus. When the first prediction was done, the word then was chosen as the most likely candidate, and it had quite high probability of 89%. When it was added to the seed, then we had another phase not seen in the training data. So the prediction gave the highest probability to the word got for 44%. See the difference, around almost 40% of the decrease here. Continuing, we can say that the probability will is likely to go down only, not above. Continuing to add words to the sentence reduces the likelihood of a match in the training data, and as such, the prediction accuracy will suffer, leading to more random feel to the words being predicted. This leads to the phenomena of AI generated content getting increasingly nonsensical over time. So there's a sci-fi short Sunspring called video that's available on YouTube. You can go around and check it out, and it's written entirely by LSTM based network like the one we are building and trained on the science fiction movie scripts. The model was given seed content and tasked with generating new script. The results were hilarious, and you'll see that while the initial content makes sense as the movie progresses. Right, so we have done with this. We'll just go through the code once in the Colab, and then we'll be working on how to extend the data set. So we have already read that we don't have enough of the training data. That's one of the reasons why it's performing poorly when predicting new words. After few times the probability is going down. So we'll understand that in the next lecture, but now we just move on to the Colab. Welcome to Google Colab. This whole collaboratory and the code is available in our GitHub repository, and the link would be in the description of this video. Right, so let's get started. First, we need the imports. So we imported TensorFlow and we got tokenizer, patch sequences, embedding LSTMs, dense and bidirectional layers, and then we got our sequential models, Adam optimizer, and NumPy as NP. Right. So we got the data as well. You can see it's separated by \n here, and then the corpus we converted into lower text, split it with \n, and we fit the corpus on text, so basically converting into tokens and the number of words we get it. Right. Next, we have the splitting of sequences that you can see. I have given you a small example as well. So if it's this the example, the split would be something like this, and we've already seen it and how it works, right? So you can see the splitting here, and then we pad the sequences as usual that we do, and using the pre-padding, you can see the sequence would look something like this, each of them having the same shape, I would say. Right, so then we have our input as x for 0 till 4, and the label would be 2 for the first one. Then, as we've discussed, we match each feature to its corresponding labels. We need the labels and the input sequence of the features. Then using slices, we just use all the rows and the columns except the last one for x's and the last column for the labels. Then we just define a model, and before that we encode the labels. So for ys, using one hot encoding, we use utils.toCategorical and we just encode our labels. And finally we have a model sequential layer, then we have embedding layer, we have bidirectional layer, and finally the dense layer. Right, we compile it with categorical cross entropy as gloss, Adam as optimizer, and matrix for accuracy. Fit it. You can see it's pretty good actually. The accuracy in the starting is low, and as we move forward, you'll see that it's still 1500 to go, right? So almost you can see that it's about 90, 93, 94%. Reaching 1500th epoch, it's 94% accuracy. So using matplotlib, we just plot the number of epochs and accuracy as well as loss. So you can see the accuracy going up steadily and the loss going down steadily. And finally, for predicting the words, we have the seed text. We convert it into tokens, pad it, and finally we use np.argmax model.predict. As I've already told you, do use this one, except rather than using predict classes one. So it's deprecated. You predict it's 3 and the word would be A. So let's see if the original text was that. So sweet Jeremy saw Dublin. So using this only, you can see that I got the seed, then I got the predicted one, then I combined those whole text and I got the next prediction. So you can see the whole line or the sentence came out to be sweet Jeremy saw Dublin to a terrace, old died nonsense asked. So you can see that to terrace old, I guess something like this. It's actually good, but not after that. So we can say that the model is turning towards being nonsensical and giving nonsensical outputs. And that's why we need to extend the data, because we have less data. So the accuracy of training might come out good because the words and the corpus, but it's not working properly for our testing and predicting. So that we'll be understanding in the next video, and then we'll try to figure out how we can improve upon this. Till then, you can just check out this whole code in the collaboratory and go to GitHub and get this whole code, run it for yourself, and you might just work out with data. You can take any sort of data that you would love to take and then check out if you can predict the next words. Till then, thank you for joining in and keep learning.